Hey, what's up? This is Mr. Bainey, and this lesson is 10.1, Scatter Plots and Trend Lines. The essential question is, how can you describe the relationship between two variables and use it to make predictions? Now, in real life, when we compare two things, two variables, uh, they're not always going to be in this perfect linear relationship that we've been dealing with. Sometimes you're going to see that these points do not lie on a straight line. It's going to kind of look like a messy graph to us. And so that's a little bit more realistic, something that we deal with. And when we have that, we can actually still make them into a linear model, as you're going to see here in a few moments. And so let's talk about some vocab first before we get into this. Um, First, in order to deal with scatter plots, we are looking at specifically two variable data, and that just means we have two different things that we're comparing. So things like air temperature versus time of the day. Okay, so air temperature could be our Y value and time of day could be our X value. And so this is all going to be organized into a scatter plot. And then correlation is how are the two variables related to each other, or are they related to each other? So um, it kind of defines it for you formally by saying that it is the strength, it's how strong they are related or not, and what happens when one increases, one variable goes up. So I'm going to give you an example here. Um, so the x-axis, for example, could be the number of hours that you study. So if you study like only 1 hour here versus if you study like, I don't know, 12 hours, then the y-axis could be your test score. So test scores down here could be a low test score, like, I don't know, 20%, and up here could be a very high test score, like 100. And so you would think about, the is the number of hours you study related to the test scores that you earn? And yeah, you would not get a perfectly straight line, but you should see that there is some sort of correlation between those two different measurements. So another example here is like, what if um, I labeled my x value as um, the amount of time that you spend on your device? Okay, so if you're on social media, Instagram, Twitter, or if you're on your playing video games or something like that. So let's say this is only if you spend about an hour on your device or on gaming, and here is if you spend, I don't know, like 12 to 14 hours on gaming or on devices and social media. Then this could be your grades, right? Or maybe your GPA or something like that. So this would be like a GPA of 0.5 up to like a GPA of 4.0, maybe up here. So you can see that if the number of time spent on your devices or gaming goes up, your GPA will likely fall and go down. So that's a negative correlation. And then no correlation means they're not related. So something like, I don't know, the your height, I could say, if that's your height, X, and Y could be your test score again. Okay, test scores are very easy to measure, so it's easy to sort of compare that with something, and you'll know that height doesn't have anything to do, it has no relationship with the test scores that you get. So those are the different scenarios that we could get. I am not going to do the explore here. It's something that you can try out for yourself if you like. You can come in and have me take a look at it. On the second page is a definition of correlation coefficient. Uh, we usually use the variable R when we're talking about correlation coefficient. It does range from -1 to +1, where 1 is a perfect negative correlation. I'm actually not going to write this down, so you can write it if you'd like. But -1 is like a perfect negative correlation, so it's all lies on one straight line, and a 1 is a perfect positive correlation. If it was in the middle, 0, it actually means no correlation. Closer to 0, you can see it says weakly correlated data will have values closer to 0. Very strong correlated data will have -1, closer to -1, or +1, depending on if it's positive or negative. Okay, so we're actually not going to worry about how we calculate R. Just know that what R could equal to based on how close the data is related. Okay, so on this next page is a very helpful graphic in understanding the R a little bit more. So you'll see on the top that R is close to -1 if it's a strong negative correlation here. R is close to +1 when it's a strong positive correlation. And likewise, it's actually going to be closer to 0 when it's more spread out, and here closer to 0 when it's more spread out, when it's a weaker. Okay, so on this fourth page, you'll see that I'm going to just quickly do these. This isn't the major part of this lesson anyway, but this is a positive correlation. You want to think about, is it a weak positive or a strong positive? So this is a weak positive correlation, so it will be a positive R value. So R is going to be bigger than 0, but R is also going to be less than 1. And so I shouldn't have written it that way, sorry. I should write it as a compound inequality. So R is going to be in between 0 and 1. It's not going to equal 0. It's definitely not going to equal 1. So something like that. Okay, so just know kind of in what general area the R could be. And so for number 3, you'll see that this all is pretty close together. My line that I'm drawing also isn't very accurate. It's just a what it could be. And R is definitely going to be negative in this case. This is a very strong correlation. So I would say something like R is in between -1 and let's say 0.5 maybe. It's pretty strong, so it's going to be closer to -1. But I'm at least, sorry, I should put -0.5. But it's just to sort of indicate that I know it's not really going to be close to 0 because it's pretty strong. Okay, now on to the more important part of this lesson is doing line of fit. So you'll definitely want to read up on this definition of what line of fit is, and also how to find line of fit. So there is actually a more complex way to find the line of fit, but we're going to use what's called a visual method. So right after I underline where it says visual method, then you can read up on that. I'm actually going to do it, so I'll show you what that looks like. Now, line of fit can also be described as line of best fit or trend line. So if you see any of those things, it all means the same thing. So I'm going to do this part B right here, and this is the a table with the boiling point of water at a specific altitude in a city. So this means that for the first one, Chicago, the city of Chicago is at an altitude of 597 feet. That's above sea level. And the boiling point of water in Chicago is 210 degrees Fahrenheit. And so you can see when the altitude increases, the boiling point of water actually goes down. So we're going to graph these because these represent points. The x is the altitude, and then the y is the boiling point of the water in Fahrenheit, degrees Fahrenheit. So Chicago, 597 feet, has a boiling point of 210, so that's about there on the graph. And I'm going to go ahead and just not talk the whole time, just going to graph it. I hope that's pretty accurate, but I only have 5 points here. On most scatter plots, you're going to have a ton more points, but they're being nice to us here and only giving us 5 points to do. So my line of best fit, this is how we're going to visually think of the line of best fit. So I have my 5 points, and you want to think about, first of all, what type of correlation this is. Is there a correlation, right? Is there a relationship between these? And you can think, yeah, it is, because you can see it when the altitude goes up, boiling point's going down, so my trend is a negative trend. It's actually going down like this. One way you could do it, I actually didn't explain it this way in class, but you can think of a very, very skinny rectangle, the skinniest rectangle that you can kind of come up with, and your line of best fit is going to kind of be inside of here. Another tip is that you want to draw your line of best fit to be as close to all of the points as possible. It does not have to go through all of the points. So don't think that is a requirement. So I am going to try to draw a straight line here that would somehow be as close to all of these points as possible. Okay, try the best I can. So it could look something like this. Um, let's see. Maybe we can move this here. There we go. So something like this. When you do this on a quiz or a test, or even on the homework assignment, you're not going to get the same exact line as another person, or even as me. So if you were to do this, you might come up with a slightly different line. Because what's next is we actually have to write the equation of this line. When we write the equation of this line of fit, the easiest way is to find those two pieces of important information, which is the slope and the y-intercept. Going to be the easiest things. So the y-intercept, in this case, I got, do this in green here, I got 211 as my y-intercept. So I got 211 here. The slope is, I can use the 211 as my y-intercept, and then I just need to find out like one other point, and then I'll be good. So I don't know, I'm going to use like this point way down here. This looks like a good, accurate point. You have to pick a point that's on your line of fit. So from here, I'm going to figure out, okay, what if I go down to do my rise and then over for my run? So that's going to tell me my slope. I went from 211 all the way down to 202. So that means I went down 9. And then I went over, how much is that? 5,500. And so you can divide. I'm actually okay if you just put that into a calculator and get some decimal. But because I don't have access to a calculator right now, I'm just going to use that as a fraction. I'm not even going to simplify it or anything. I don't think it actually does simplify. But our equation is going to be y equals m times x plus b. And I know my m, I know that my m is a slope and that the b is the y-intercept. So my equation is y equals negative 9 over 5,500. That's a slope, right? Times x plus 211. And that's the equation of the line of fit. You're going to get some pretty ugly numbers, especially the slope, when you're dealing with graphs like this with some really big numbers. But that's okay. It's okay because the line of fit is only supposed to be just a very general estimation of what this trend looks like. And this is going to help us make predictions. Like I could ask something like, can you predict what the boiling point of water is at an altitude of 3,000 feet? So if we live somewhere, now this is not true, but if Elk Grove was at an altitude of 3,000 feet, I can go look at this line of fit and see that we would have to boil water at 206 degrees Fahrenheit. Okay. So I would like you to try this before you see the solution if you're comfortable. I'm going to go ahead and start plotting these points. So you have 0, 2.1, 1, 4.3, 4, 8.1, and 5, 10.2. This looks like a very strong positive correlation. So my line It's going to look something like this. Something like that. And so my equation, right, y equals mx plus b. I need to find the m and the b. That's the slope and the y-intercept. My y-intercept, I don't know, something like 2.3, right? 2.1, 2.2, 2.3, 2.4. Those are all will probably be acceptable. When I do my answer keys, I'm going to be looking at a range of acceptable y-intercepts and also a range of acceptable slopes. So it doesn't need to be exact. To find our slope, we got to figure out some nice points here. If I use the point 0, 2.3, then I can go up to, it looks like, I mean, I could use other points, but I can see that this line is going straight across this point right here. What point is this? This is 3, 7.3. It's right here. So 3, 7.3. And so to find the slope, the rise is, oh, it actually gives me a nice one. So 7.3 minus 2.3 is going to tell me my rise. And then this is a slope. And then 3 minus 0 is going to tell me my run. So this ends up being 5 over 3. Yeah, it gives me a pretty nice slope. So slope of 5 over 3, and I am done. So we can now use this equation to make predictions, just as I mentioned in the previous one. So we're going to use the equation that we made in the your turn number 5 to predict how tall the tree is going to be 10 years after she planted it. So I'm going to actually use the equation. I remember what it is. It is y equals 5/3 x plus 2.3. Okay, so in 10 years, that means that I'm going to do y equals 5/3 times, whoops, times 10 plus 2.3. And that's not going to come out to a super nice number, but you know, since we're doing predictions and a line of fit isn't going to give us an exact answer regardless, then rounding it to decimals is perfectly fine. So you're going to get something like 50 over 3, which is, what is that? 5/3 is already 1.6 or 1.7. So let's say it's about 17.7, and it'll come out to about maybe 20 feet. Okay, so hopefully you get that if you actually work it out, put it in your calculator. But that's how you would use the equation to make the predictions. Okay, and that's going to be it for this lesson. I'm going to cut it a little bit short because the last part of this, you could read through it. It's just determining if the correlation is actually if one variable, the change in one variable is actually caused by the change in the other variable. And so that's not something that we're going to look at that closely, but it is good stuff to know. Okay, so I hope this was helpful. Have a great day, and thank you so much for watching.